Hi, everybody. Welcome to the fifth edition of Optimal Control and Reinforcement Learning 16745, affectionately known as OCRL. Let me get rid of this thing. It's annoying. I'm Zach, your fearless leader for the semester, and you can call me Zach. And this is the rest of our illustrious crew. They're all standing back there. You guys can say a quick hi. So we've got JJ back there, who's sort of the senior TA, so to speak. He's TA'd the class before. Have you done this twice before? Twice before. So this is third round TAing. So excellent experience. We got John back there, sort of first year PhD student, but been around the lab for a couple of years and has done a bunch of this stuff for a while. We've got Fausto, who's TA'd the class before. Got Arun, who's sick today, but will be around in general. And senior PhD student working on this kind of stuff. And then we got Ashley back there, who took the class last year, who's been in lab for a couple of years. So everybody in the, on the TA team there has either TA'd the class before or is working actively in this kind of area for their research. So super solid folks who know this stuff really well, who should be able to help you out in office hours, homeworks, and project stuff. And obviously you can always bug me. Okay, so that's the crew. They're all here except for Arun, who got the flu, unfortunately. And definitely sort of don't be a stranger and come talk to us. He's making a buzzing noise. It's kind of right over my head and is very irritating. Okay, so let's give a quick, kind of just overview of what all this stuff's about. Like, what is optimal control for? Why do we care about this stuff? So it kind of all begins maybe like 60, 70 years ago with the space race. That's kind of when this subject really grew up and became a thing. And originally, the kind of original use cases for optimal control were rocket trajectories. So some of the big names in this game, one of the biggest names is Pontryagin. Who's heard of Pontryagin before? Any hands? Yeah, so Pontryagin minimum or maximum principle, depending on if you like to minimize or maximize. The great divide between RL and optimal control. Take your pick. But so Pontryagin was a Russian guy, Russian mathematician, and he was working on this stuff in the 50s. And basically right away, this stuff was used by both space programs to figure out how to design rocket trajectories and to do things like fly from the Earth to the moon. Or that picture there is actually the trajectory that Mars 2020, the latest Mars mission, took to get to Mars. So this stuff is very actively used still today in this context. And folks at JPL, who we do some work with, for example, who design those sorts of trajectories, use kind of state-of-the-art co-location techniques that we're going to talk about in the class to design stuff like that, to figure out how to design interplanetary trajectories for spacecraft. Sort of veering away a little bit from this classical case, but still very much in the aerospace vein. Like another application for this stuff that's super current still, but from the traditional aerospace end of things is landing rockets. Everyone's seen SpaceX, land these things on barges. Anyone know how they do this? Yeah.
There's like some investigation thing they do.
Yeah. So this was a seminal result about 10 years ago in control, in aerospace control. This guy, Lars Blackmore, another guy named Bechet Achikmache. Lars now is the kind of GNC, head of GNC, basically head of control stuff at SpaceX now. And Bechet is a professor at University of Washington now, but they were both at JPL at the time, like 10 years ago. They figured out a really clever trick to turn this nonlinear, non-convex problem into to relax it into a convex problem. So we're going to talk about this in the class. We're actually going to go through this as a case study later in the semester and show you exactly how this works. But basically, it's a magic math trick that sort of transforms this problem exactly from a nonlinear problem that's hard to solve into a convex problem that's easy to solve, and you can give all kinds of guarantees for, and you can solve fast online. So this was like a beautiful, theory result that ended up really quickly getting ported over into real applications. So these guys use it to land, and also JPL uses this stuff to land on Mars. So really cool application where like a theoretical result, really quickly went from like, academic paper to like landing rockets, which is kind of awesome. So that's convex MPC, which we're going to talk a bunch about. Autonomous driving. So everyone's seen this stuff before. there's lots of, like buzz about how everyone's using, deep learning to do this stuff. That's mostly on the perception side, and sort of modeling human behavior ends of things. But the actual driving of the car in almost all cases is still MPC. So people are doing nonlinear MPC with simple single track bicycle models for this stuff. Um, they're using all this kind of learning stuff to do perception, figure out where the other cars are, predict what human drivers are going to do, and feed that in to an MPC stack at the end of the day that's actually planning trajectories, reasoning about the dynamics of the car, tire friction, all that kind of stuff, and doing the actual driving. Yeah, so there's that. What else we got? And then yeah, everyone's seeing this stuff too. This is now getting kind of old, but and more recently there's been a lot of like RL results that people have, really gotten RL controllers to work super well on these kind of robots. But the default controllers still on those quadrupeds are MPC, and there's a bunch of tricks in there to deal with non-smooth contacts and like how the feet touch the ground and all this kind of stuff that we're going to talk about later in class. So lots of tricks, but at the end of the day, this boils down to some pretty simple MPC with a bunch of heuristics for most of the legged robot stuff. And yeah, the MIT Cheetah, like really, Songbae Kim at MIT really pioneered getting these things to work. I mean, now these things are basically a solved problem and you can just buy them, but like 10 years ago, this was, not really possible. So it's really come a long way in a relatively short amount of time. And mostly still MPC. Just in the last year or two, RL controllers have started to catch up to the MPC stuff and in some cases outperform MPC. But this is all MPC. Okay, so we're going to talk about that stuff later in the class. And then obviously this stuff, humanoids. I'm actually went looking for a new, everyone's seen the new Atlas, the electric one. There aren't very impressive demo videos of new Atlas out yet though. They're doing like factory manipulation stuff that just isn't that cool looking. So this is like one of the cooler ones, recent-ish cool ones, of them doing like pretty dynamic manipulation and running around and backflips and all the good stuff that we've all seen on the old Atlas. No new Atlas videos doing this kind of stuff yet. But yeah, this stuff is all nonlinear MPC. So this is them doing basically really hardcore nonlinear MPC with a whole body model of the robot, models of objects in the world, models of the contact dynamics, contact interactions between the robot and the world, and essentially just solving these like really pretty gnarly, pretty big nonlinear optimization problems at like hundreds of hertz in real time and running on the robot. So we'll talk a little bit about how this gets done too. Yeah. Any questions about any of this stuff? This is all the fun stuff. Just want to tease all the good stuff. So I think pretty much everything I just showed you, we're going to do actually later in the semester, we're going to do case studies where I'm going to give you guys papers, like recent-ish papers on all of these kind of really cool, recent-ish robotics applications of this stuff. And we'll go through kind of some of the secret sauce, how it works, and give you a fairly decent idea of how this stuff. So by the end of the semester, at least at a, highish level, like, I mean, there's lots of details, obviously, and the implementation work is tricky on all this stuff, but at least at a fairly in-depth level, you'll understand how all this stuff gets done, like how to implement, in principle, how to implement controllers for these kind of systems, which is pretty awesome. Okay, so, and then just to kind of like looking ahead, right? Like we do this stuff in our lab for our research, kind of where are the current challenges and where's the kind of the hard stuff now? Like that stuff I just showed you is all kind of last 10 years, of like awesome stuff. Where are we looking now into the future? I'd say contact interactions are still a big deal. Like planning multi-contact, long horizon, say manipulation or local manipulation things, still really hard. And that comes down to the fact that these contact dynamics where you're making and breaking contact are non-differentiable. So all the nice gradient-based optimization things we like to do kind of break. And you can think about this a few ways. You can think about it as like, the limit of like a very stiff but smooth nonlinear process, which is gross if you try to do gradient stuff. Or you can think about it as like a discrete combinatorial optimization kind of graph searchy thing. Both of those are bad for different reasons. The graph search kind of setup blows up combinatorially, like exponentially in the size of the problem and becomes intractable pretty quickly. The smoothed version ends up being ill-conditioned and stiff in all kinds of bad ways and suffering from local optima. So that's all bad. So no one really has a great answer for how to generally solve those problems. And everything ends up being kind of hand-coded heuristics and special case engineering solutions to those problems, I would say still, whether it's RL or, MPC or whatever, like lots of heuristics, lots of hand tuning to get that stuff done. Or you just punt and get humans to teleop everything hundreds of times and do imitation learning or whatever, which seems very unsatisfying to me. Like we've given up on actually solving motion planning now. Uh, I don't know. Let's see. Dealing with high dimensional systems, I'd say like, so this is like soft robots, right? Deformable things, fluids, squishy stuff. This is really hard. Like if you try to model it, you end up, or simulate it, right? You end up with PDEs, really high dimensional mesh sort of things or particle things. All of it's gigantic and hard to simulate. So if you want to train something in sim, super hard to simulate. Usually doing it in the real world is too messy and not reproducible enough to get enough data. Writing down the models, right? It's too big often it's too big to simulate in real time, even these kind of things. So this is still a really hard thing. And then I think there's still like a really rich intersection between model-based control and reinforcement learning. And this goes way back. Like, in my opinion, these are really the same thing. And it's like a continuum of how much prior information you want to use, how much modeling you want to do, um, how much of a black box you want to assume your simulator is. It's kind of right. It exists on a big fuzzy continuum, and I think we still haven't quite figured out the sweet spot in here for most applications. Like I think the legged robot stuff I showed you is a case in point, right? Like we've got people doing MPC for the last 10 years, and then now we've got like people doing RL, and they're coming from two completely different camps. Like the MPC folks are coming from engineering, like mechanical and electrical engineering, and the RL folks are coming from computer science. And the only reason that's started to work is now there's commodity hardware that they can buy because they don't know how to do hardware generally. Not to like, these are people coming from like more pure computer science, and like these are like, basically there's been no middle ground between these yet, I think. And this is, to me, also seems like there's a real opportunity there. So kind of encourage all of you guys to learn both sides of this, learn both and try to figure out um, the right ways to use the right tool for the job, right? And don't kind of discriminate, I would say. And then, yeah, like a big one right now, especially in the learning-based control world where we're doing data-driven stuff and we don't have good models necessarily, is trying to get safety guarantees. Like one of the big things about classical optimal control, we have models and we do, optimization, is that in a lot of cases we can give hard safety guarantees for stuff, like guaranteeing you're not going to, run over a pedestrian or crash or blow up your rocket, this kind of stuff. We can give fairly rigorous mathematical guarantees for these controllers that they're not going to do bad stuff in most cases, right? Modulo some assumptions, but there's like things that can make you feel confident about the performance and safety of your system coming out of these model-based optimization approaches. Whereas, pure data-driven RL approaches really, you don't have that. And I think this is a real frontier area of trying to like, this is one way where like there's really I think could be some real benefit to bridging the gaps here between like RL stuff and model-based control stuff in trying to see if we can figure out good ways of getting back some of the guarantees that we sometimes can have with classical stuff. And then, yeah, another one that's super fun that this I think should play a video, maybe, I guess not, is dealing with like kind of other agents that are not cooperative, like which shows up in particular in autonomous driving. We have to reason about other human drivers, right? That might act irrationally, that might do crazy things that are unpredictable. Like how do you deal with that? And that's kind of tied into the safety thing as well, but it kind of another angle on this where you're not just dealing with dynamics and try to be safe with respect to collisions with fixed obstacles, but you have to think about like this driver might do something totally crazy. They might not use their turn signal like they're supposed to. They might, whatever, right? So I think that's a pretty interesting area as well. Yeah, thoughts, questions about any of this stuff? It's just like stuff Zach thinks is cool, but hopefully you do too soon enough. All right, so what are we doing here? What's like the class kind of be about? Number one, it's about, so it's optimal control. So the optimal part should kind of tell you there's gonna be a lot of optimization. Basically, I'd say we're talking about optimization-based control techniques writ large. So that's, gonna be, we're gonna start out with like an overview of optimization and kind of what that's all about. We're gonna talk about dynamics a little bit, then you basically put those together, try to control interesting robotic systems. We'll talk a little bit about, We're going to kind of like do some basic stuff and try to get you grounded in some of the fundamentals. And then we're going to kind of dabble in a few other interesting topics, talk about some data-driven stuff, talk about a tiny bit of RL stuff, talk about some sample-based stuff like MPPI that you might have heard of that's kind of hot. So we're going to kind of, yeah, and then we're going to do some case studies where we dig in on a few like really kind of juicy state-of-the-art, legged robots, autonomous driving, these kind of topics, and show you some of the secret sauce under the hood and some of those things. So that's what we're going to do. The focus is very application driven, very roboticsy. We're going to really focus on like how to do optimal control, like practically, rather than like super deep theorem proof lemma type stuff. So there's going to be homeworks. They're going to be all about implementing controllers in sim, like making the algorithms work, getting stuff to happen, rather than like proving stuff, right? So coding assignments, not really any kind of theory, math, prove stuff type assignments. And then the big thing is, so the homeworks are going to kind of go every couple of weeks, beginning of the semester. And so by like week, say 9 or 10, we're done with homework. And so the last month of the course, there's not going to be any homework. We're going to be kind of in case study mode where we're just showing you cool stuff. And the idea there is there's going to be a course project. This is one of my favorite things about the class. So, you should really embrace the project. The idea is, most of you guys are grad students and hopefully engaged in some kind of research or some kind of, master's project, whatever it is. So the idea here is like, hopefully you're taking this because not only are you into it, but it sort of overlaps with, what else you're doing in life with your research, your projects. So the idea is to like try to bring that into the class and use this as an opportunity to like use the stuff in class, the techniques we're learning, and apply it to your research or whatever you're doing, to your master's project, that kind of thing. So you get to do this in groups. I think I nominally cap it at 5. I strongly suggest getting together with some other folks. Don't do it by yourself. If you really want to do it by yourself and you're a PhD student, you've got your own research already and you're already kind of into it, that's fine in principle. But I'd suggest, like in general, you should try to buddy up with some people. It makes the whole thing more fun and generally makes your life better. So highly recommend getting together with some folks. I think 5 is probably about as big as makes sense usually with these kind of things. Otherwise, it's too easy to get like kind of lost in the sauce with too many people. And you end up having to do project management. I don't like project management, so we're going to try to keep it capped there. And yeah, do something cool. That's basically it. As far as like how that's going to work, on the first homework, there's going to be a project proposal where you're going to have to like tell me what you want to do, and I'm going to kind of ask you at a high level what you want to do, ask you for a few references, make sure you've like looked into this a little bit, and then after that comes back, I'm going to give each group a little bit of feedback on their project and basically try to guide you and scope your project into something that I think is doable in the amount of time that you've got. So I'll give you that feedback, and then we're going to have each group is going to meet with me one-on-one to talk about the project scope, the feedback, and try to make sure we're dialed in and that everyone's on the same page as far as like expectations and like that it's a good scope, that it's practical to actually get it done in a couple months, and that you're not like biting off more than you could chew, that kind of thing. That's how I've done it every year. It's tended to work pretty well. And the idea is that the format of the project is basically going to look like a conference paper. We're going to try to model it on like an ICRA paper, basically, and I'm going to kind of have you write it up using that like LaTeX template. More or less, that's kind of what we're aiming for, like a 6-page conference paper flavored thing. Many of the course projects end up becoming conference papers. So if you're a PhD student and like that's kind of the mode you're in, great, grab something from your research. Let's do something cool, and then you can publish it at the end. We've had one project from last year turn into a startup that got venture funded, which was awesome. It was autonomous sailing for like cargo ships, which I thought was amazing. They just went public and like announced their whole thing. So that was kind of awesome. It was like a thing to come out of the class. So yeah, definitely I think the projects, it's kind of what you make it, but they can be really cool. They can turn into, like, we've had tons of research papers come out of these, one startup, right? So definitely like I think like this is like where you can really get something cool out of this, right? If you're into this stuff, like do something cool. It can be kind of anything you want, right? So think big, embrace it, and just like it's really open-ended. So do something you really are into and that you think is cool. Like that's kind of the bottom line. And we'll give you like guidance and support to like kind of get there. Be creative. Yeah. Okay, so that's that. Any question about this stuff in terms of what we're doing, what it's about? Okay, everyone's cool on this stuff. All right, so then some like basic logistics stuff. Lectures, you obviously figured this out, so we're here in person. We're also gonna live stream it on Zoom. So there's a few people on Zoom who have apparently figured this out. The one caveat, so basically the message there is if if you're sick, definitely don't show up. If you've got other stuff going on, if you got to travel, whatever, life happens, it's okay. I'm not going to be, mad if, the room's half empty and, it's okay. You can do Zoom. I'm also going to record the lectures and we have a YouTube channel. So they get posted on YouTube generally within 24 hours. So you can always go back and watch it later. I think that's also nice because you can kind of engage more and not be struggling to write notes. I also do all the notes for class on my iPad. And then those notes also get posted as PDFs. So you can get the videos on YouTube and the PDFs. And I do a lot of live coding in Jupyter Notebooks. The Jupyter Notebooks also get posted on GitHub. So everything is posted. You can go back and read the notes. Caveat that my handwriting is at times not the best. So that's the one possible wrinkle there. But you can see the code, you can rewatch the video, all that kind of good stuff. Hopefully that helps you out. And yeah, like I said, if you have to miss lecture, it's all there. You can always find the stuff. Yeah, there's gonna be 4 homeworks. They're distributed on GitHub. So GitHub is basically a required thing for you to use. Has anyone here not used GitHub before? Amazing. Okay, great. Occasionally we have some folks who are like more mechy who have not used GitHub before, but that's great. So GitHub is where the things get posted. That's where the code from like lecture notebooks is going to be. That's where and then grades or sorry, the homework's handed in through Gradescope. There's a whole process we figured out the last couple of years for this, where you're essentially the homework assignments are all in Jupyter Notebooks, and then you're gonna basically print the Jupyter Notebook out as a PDF and submit that to Gradescope. We found that works better. We had people submitting the Jupyter code notebooks as the assignments and then tried auto grading these things for a while. And that turned into a mess with like dependency issues and stuff like that. So we're not doing that anymore. And then, yeah, we're gonna have office hours. The TAs will have office hours. I will have office hours. My kind of historically, what I've done is tried to do office hours basically like before or after class. I'm here anyway. And so I'm going to probably do that. We'll have a little bit before class, a little bit after class, every lecture. So that's what I'll do. We'll probably do a little bit by appointment. Like if you have scheduling issues and you can't make those times because you have stuff before and after, talk to me obviously, and we'll probably do something else too. The TAs will do, a broad range, and we'll have both Zoom and in-person options, and they'll be kind of spread throughout the week. Did you guys want to do a schedule poll, or are you just going to kind of roll with it and Oh, it's up to you guys. I mean, you're gonna have to do it. So, um, okay, yeah. So I guess JJ is gonna throw up a poll so you can like put in your availability, and we'll try to like impedance match the schedule of the office hours to kind of work with the most possible people. We'll also probably we're gonna add extra TA support for office hours like around homework deadlines. That's what happens inevitably. We've learned so that'll all be, I think, should be good. And then what I'll do too is I think generally my office hours are going to be more for projects. It's more project focused. So basically homework questions, you go to the TAs. More kind of researchy or project stuff. I'm going to try to like interface with all of you guys pretty actively on the projects. So I'm going to have project consulting hours definitely towards the second half of the semester. And that's kind of what I really want to engage with you guys on, make sure you're kind of on the right path with that stuff. So we'll set those up. They're not up yet, but they will be set up. We have a course calendar for all that stuff. It's easy to find. There'll be Zoom links in there too, all that good stuff. Okay. Questions about any of this? Okay, so a couple things. Number one, there's a course survey, like a Google form for you guys to fill out. You can do it now if you want, or you can do it, try to do it today. It's just like a quick thing to like gauge some stuff for me. And we're gonna have Piazza for like all kind of regular course communication stuff. So don't use email. I used to use Slack for the class, but it got too big and we couldn't have like 150 people on Slack. It turned into a mess. So now Piazza is what we're doing. So yeah, basically, if you want to get in touch with any of the TAs, don't do email, whatever. Try to keep it here. And also try generally to like not DM the teaching staff if it's a homework question, especially. What ends up happening is if you DM us and we respond, like 10 other people are going to have the same question. So it's much better to do it in a public thread. So if you have a question about something, pretty much guarantee you like 10% or more of the class is going to have the same question. So please keep the discussions public. If you've got some other issue that's like personal or whatever, totally fine to DM or whatever. But otherwise, if it's like technical question, homework question, whatever, do it in a public thread so that like it's all there so everybody else can also benefit from the same conversations. We don't have to like repeat it 10 times. So that's where that stuff is. Let's pull it up real quick and we'll just kind of go through a few things. Okay, so few relevant things. So this is the GitHub. We have a GitHub org for the class, and then homeworks and lecture notebooks and all that good stuff is going to be posted in here. Let me see if I can. It's really awkward to see this over here. I'll try moving this now. Okay, so cool. So here's the org. Syllabus is in here. You can go look at this. And this will get updated as we go as stuff changes. So you can keep it like basically the most current version of this is always in this repo link. So you can always look at it. Basic info, here's our contact info, whatever. Stuff we've just talked about. Kind of what we're talking about in the course. So, we're going to talk a little bit about dynamics. That's coming up first. We're going to talk about kind of the really basic classic control stuff for linear systems, kind of LQR. We're going to do trajectory optimization, convex MPC, talk about like sort of uncertainty and stochasticity a little bit, that kind of stuff, some data-driven stuff, all that good stuff. There's no book. We've got the website. We've got like now like 4 years of prior course notes and videos you can refer to. Also, the last couple of years, we had a really, really awesome senior PhD student, TA named Kevin, who did his own recitations in addition to the lectures. Those are also up on the YouTube channel, and they're really good. Kevin's awesome. And he basically, like did his own sort of spin and filled in some of the gaps in what I talked about in class. So highly recommend going and checking those videos out as well. And we will kind of like, those are already out there. You can find them. And we're going to kind of push them out onto the website like every week to go along with that and kind of encourage you to check that stuff out too. I think Kevin was like both very good and also like he was doing a lot of office hours. So we got to see kind of what people are struggling with a little bit more. So he kind of beefed up certain things in the recitation section. So definitely encourage you to check that stuff out. That's all on the website. Homework stuff. We're going to do homework every 2 weeks. In the beginning, there's gonna be 4 assignments, sort of 5-ish. There's a homework 0, which is just to get yourself set up on GitHub, make sure you know how to do stuff and use Jupyter. It's that kind of thing. So it's not really a real assignment. So you just have to do it to get processes figured out, so that we're not dealing with like midnight submission issues like when we actually do homework. So that's gonna happen. Project stuff, this is kind of like roughly the story I just said. Like we're going to try to do it in the style of like an ICRA or IROS conference paper. And you're going to have we were doing presentations, but the class got too big to have everyone do a presentation and end up being like crazy lightning talk vibes, and we still went over. So we did, starting last year, is a poster session. So the last week of class, the last 2 classes are going to be poster sessions. So everyone's going to come and set up in here with a poster, and we'll like do, the teaching staff and everybody else too will like make the round and, talk about what you did. So there'll be a part of the grade that's like that, basically, poster stuff and how the, interaction, and like I'll grill you a little bit basically and see how that goes. And then, yeah, just kind of the written report is basically the rest of the grade. And the poster session's fun. And we have a tradition of cookies, so that's good. So come out for the poster session. Grade is like heavily weighted to the project. It's basically half project, half homework, and then like a little bit here. So we're gonna have weekly quizzes also. These are like super little, basically like multiple choice questions just to gauge how things are going and kind of force you to like pay attention to the lectures every week, not get behind. They're super quick, like they shouldn't take you more than 10 minutes. And so that's a little part of the grade, basically just a completion thing. Like you should take it seriously and do it, but it's not like a big deal. And then, yeah, kind of this fuzzy participation thing, which is basically just a way for me to nudge your grade a little bit if I feel like you deserve it at the end. So the story there is, participation, you don't have to show up every week. As I said, like you can do the YouTube thing, but it's like, this could be, showing up to office hours, talking to me about your project, whatever. Like you have to engage basically. So if I know who you are and I've seen you a few times throughout the semester, thumbs up. If you never show up to anything and I don't know your name and I've never seen you at the end of the semester, like when it's grading time, I might not give you a little bump, basically, is what that's about. So that's basically what that's about. Basically, if you've shown up to stuff and we know you, then you'll probably get a good participation grade. Okay, generic course policy stuff. I think the main thing in here that's worth noting is homework like late days. I think have a general like late day. I think we have like a late day budget situation, which I think is pretty standard. I think nominally like six days that you can use in any combination you want on the four homeworks. Um, yeah. And yeah, if you have some kind of personal situation, you know, like I'm not going to be crazy about this, like come talk to me if something's going on. But generally, like, yeah, you have 6 free days to be late. You can use them all together. You can use one at a time. You can do whatever you want on homeworks and stuff. You cannot use them on the project. The reason being is I make the poster stuff is the last week of class. It is what it is. And then the actual report deadline, I basically push back as late as possible before the grading deadline that I have to submit your grades on. So I can't push it back anymore. I'm just going to give you as much time as I can. And then the deadline is literally a few days before I have to submit final grades. So it's like just enough time for me to go through them before I have to submit your grade. So there's no late option on that. If you're late on that, I can't help you. And, it is what it is. Okay. Any question about any of this stuff? Yeah. Uh, I'll have to think about that. TBD. I don't have I think they're just days. I think it's just calendar days. I don't think we're doing, yeah. We, yeah. Okay. That's a good question. Fair question. And then, yeah, there's kind of a schedule in here. Basically topics, we mostly stay to the schedule. I'd say there's going to be a little bit of like, and then this is spring break and this is a random day off or something on the official CMU calendar. I don't know. I forget what it is. Homeworks are going to they're going to go out Thursdays and be due 2 weeks on Thursday, like midnight or whatever. So that's that. That's where the homeworks are. There's a survey today, which you should do like today. It'll take you 2 minutes. And there's a homework 0 that's going to go out this Thursday. Are we going to make that next Thursday? 1 week? Yeah, so homework 0 is a 1 week deal. It's not a real homework assignment. It's like do you know how to use GitHub? Do you know how to actually like clone a repo? Do you know how to, submit to Gradescope the way we want you to, blah, blah, blah. So it shouldn't take you very long. It's just to iron out processes to make sure that like there's no serious red flags and that it's basically forcing you to get all that figured out before we actually start doing real homework. So that we don't have any like crazy last minute, my GitHub stuff is broken or I don't know how to use Jupyter or whatever before the homework deadline. Okay. Yeah. Oh yeah, this is a good thing that we should definitely talk about. So let me see. There's a few other things to talk about too, but yeah, so all the course content is going to be in Julia. We're a Julia lab. Sorry if you're not into that. If you have not used Julia, it's basically like halfway between MATLAB and Python. So if you've used either MATLAB or Python, you should be completely fine. It's really easy to pick up. Shouldn't be a big deal. The reason we use it is, well, number one, we use it a lot in our lab. Number two, it's like, I hate NumPy. Sorry, the matrix syntax is gross. It has more MATLAB flavored matrix syntax, which is just way cleaner and nicer. So doing matrix math in Julia is way nicer. It also has built-in auto diffing out of the box, which is really nice. You never have to handwrite Jacobians. You just don't have to think about it. You don't have to use another toolbox. You never have to write a Jacobian by hand again in your life. So we use that heavily in the class, which is super nice. So I think honestly, it's the nicest, thing for everybody. So that's what we're doing. Again, yeah, like there'll be a little bit of this on the homework 0, but it's not a big deal. Like if you've coded in MATLAB or Python, like it should be 0 issues. It's still in Jupyter. So like if you're used to Jupyter notebooks with Python, same setup there, slightly different syntax, but like it shouldn't be a big deal. And we're going to give you, notebooks with like fill in the blank algorithm blocks. So like that part, it's like most of the course stuff is going to be like doing matrix math. So we're not going to like force you to do anything weird with Julia, like package manager stuff or like advanced language features. So none of that should be an issue. Is basically just math, questions about that. Oh yeah, one other note. Yeah, so we have a sort of policy in the class of like using the latest LTS release of Julia. So at this point, that's 1.10. There is a newer 1.11 release, but it's not the LTS, like long-term support release. So don't use that one. There are occasionally compatibility issues. So use the LTS release. This is all going to be made clear in the homework 0, where we're going to force you to install this and do all the right things. Basically, just use LTS, use all the stock stuff. One of the really nice things about Julia also has a really good package manager that versions the packages. So when we give you the homework assignments, they're all going to be versioned with the correct versions of the packages to use for everything. So like, as long as you follow the instructions, it shouldn't matter what platform you're on. If you use the LTS release and just like git clone the repos for the homework, it should automatically install all the exact same versions of all the packages that we intended when we wrote the homework. So there shouldn't be any compatibility issues as long as you follow the instructions. So just do it the right way. Don't use weird other versions of things, and just follow the recipes, and life is good. Questions about that? Cool. Yeah. So it's, Windows, Mac, Linux, whatever is fine. Like all the stuff should work. No problem. Okay. Let's see. So yeah, schedule stuff. It's probably, there's going to be a little bit of fuzzy stuff down here where things might change a little bit. The biggest thing is that this is not movable. There's kind of one free lecture floating around, so there might be a little bit of, I might actually poll you guys for like selected topics for some of the case studies later on. We'll see what happens. But the beginning, the first half is like pretty fixed, I would say. So that stuff's all kind of what we're going to do. Okay, questions about this? Yeah. No, I mean, that's sort of very, like, I would say that's not quite optimal control. That's more like classical, linear systemsy stuff. We'll definitely talk about stability. And we'll talk about like kind of Lyapunov stuff and classical, these kind of things. We're not really going to do like the H infinity robust control stuff. I think it's like far enough off the beaten path of kind of the main thrust of the course that it's like different math, and it's kind of too much of a lift, I think, to cover it really, but it's cool stuff. We'll talk a little, I'll do a little teaser, kind of like background overview on it, and point you to some references if you're into it. But yeah, I'm not gonna go deep in it, unfortunately. Any other questions about anything? Oh yeah, there's some stuff to talk about here. Okay, so Piazza, you guys know about this. You should get on the course Piazza. This is where all the communication is going to happen. What else? There's a canvas that we're basically not going to use. So it's there because it has to be there, apparently, per CMU rules. It just has pointers to all the other things, including course website. Definitely go there. That has pointers to everything. Survey, go do that. Piazza, yes. Zoom link for lecture. Like, please don't post this publicly, because we've gotten Zoom bombed in the past, so now I keep it behind a CMU login. I used to just make it free for all, whatever, and then we had some issues, so I don't do that anymore. Let's see, office hours will be Zoom and in person. Syllabus I showed you. Oh yeah, also this is full. So we have an anonymous, so the survey I just gave you is a Google form that does like log email addresses. This one is if at any point in the semester you have something to complain about or whatever, and you don't feel comfortable yelling at me, which you should feel comfortable doing, there's this anonymous feedback Google form where you can just like say anything you want. It does not log your email address or anything like that. I promise. It doesn't require a CMU login, just a blank text box. So you should feel free to throw anything you want in there if you feel, compelled. That exists. I do reserve the right to display said feedback in class. So it's totally anonymous. No one will know who you are, but they might read the feedback. That's the only caveat. Yeah. Okay, yeah, thanks. So your grade, we're using it for grading. So the grades will show up in there and the quizzes will show up in there. Thanks for that. Yeah. We generally don't use too many of the features in there though. Okay, what's this? Let's see. This we don't need. Anonymous feedback form, that's that. This is the course survey, which you guys should do. Some just like questions about your background and kind of what you're into. For my own notification syllabus, we already talked about. Okay, I think that's it for logistics-y stuff. Oh yeah, website, that's good too. Okay. Can't see anything over here. Okay, so website. This is here. It has links to all the things that are relevant. It has the syllabus here. The kind of really relevant things, I think, are the GitHub, which we talked about. These is last year's, so the lecture notebooks from the last few years are up here already for you to refer to. Homeworks will go up here, syllabus is here, et cetera, et cetera. The lecture notebooks repo is here. So this is going to get filled in. So like after today, there'll be lecture 1 with stuff from today. So everything's like up here. And then YouTube so we'll fix this link right now. It just goes to the lab one, but there's a playlist for the class. You can find last year's playlist here. So this is like, all the lectures from last year are already up here. You can go for that if you want to. I'll post them as we go. And then the other one, yeah, the Kevin's recitations are also in here. So if you go through, maybe we should make a separate playlist for those, but, okay, cool. I think I added them to the playlist, too, but we'll kind of like thread those into the, as we go kind of thing. Okay, so I think that's everything. Anything else I forgot? Course calendar is on the website as well. That's where kind of office hours and stuff will be posted on this Google Calendar. I used to also use it for appointment signups for me for project consulting hours, but Google removed that feature from Google Calendar. So now I have to find a different way to get calendar sign up slots. TBD on that. We'll work it out. Okay, cool. Yes.
Do we need to bring like a laptop or can we fill that?
You don't have to do it in class. You can do it after class. They'll go out you'll have like a day to do it, like 24 hours or something. Yeah, you can absolutely do it on your phone in class if you want to. It shouldn't take more than 10 minutes. It's gonna be like multiple choice, whatever, just kind of really basic stuff. Okay, I think that is it. I now have to figure out how to get in my little iPad, which is super annoying. Hey, it worked. Okay, cool. Sorry for I did not get this quite set up. Blah, blah, blah. Give me a sec on the iPad. And then we'll actually do real stuff.
You need to allow everyone.
Sorry?
You can pop like the window to allow it.
Oh,
Maybe only on that screen.
there we go. Yeah, thanks. This is complicated. All right. Need to. Okay, so yay. It's working. You'd be amazed at how much can go wrong with getting an iPad screen mirrored onto a projector. Let's see. That's good. That's good. Oh, God damn it. Now GoodNotes wants me to log in again for it to let me use GoodNotes.
You're for the record, you're logging in like wow.
Yeah. I don't know, man. It's very annoying. All right. Don't look at my password. God damn it. Two-step verification to use the GoodNotes app. Of course. Very secure. Okay. All right. We're in business. Okay. Thank you for your patience on that. So, we are going to ease into things by talking about some dynamic stuff. So who's taken a dynamics course? Like when I say dynamics, I mean like, F equals MA stuff maybe, but then like a little pass at like say Lagrangian mechanics-y stuff. Show of hands quick. So like half-ish. Okay, cool. So we're gonna do like a very, very abbreviated crash course in just enough dynamics to be dangerous for the purposes of like doing control stuff in the class. I'm not going to expect you to like derive, the dynamics of a double pendulum or write down the Lagrangian of some robot system or whatever. We're going to give you the dynamics in the class. I'm just going to like do a quick, like really fast crash course so you like know enough to like be functional in the class. Sound good? Okay, so first thing we're going to talk about is like the most generic continuous time dynamics. So when we say dynamics, generically, this is kind of what we mean. This is the most general or kind of generic form of this stuff for a smooth system. This is important. When we say smooth, anyone have any ideas like what non-smooth would be? Kind of hinted at it. It shows up a lot in robotics. So this is why I caveat this. Like when you take a dynamics class, often they're just like, oh yeah, ODEs, F equals MA, Lagrangian, everything's good. Turns out in robotics, there's tons of stuff where that doesn't work. The reason is that we often in robotics have contact mechanics where you have like feet hitting the ground, a gripper grasping an object. When you make and break contact, that's fundamentally non-smooth. So technically speaking, F equals MA doesn't apply when I do this. At the instant when my foot slams into the ground and I have this discontinuous impact, that actually can't be written as an ODE. So fun facts. Life is hard, it turns out. So there's some, we'll talk a little bit more about that, but just know this is like everything except when you're slamming into other objects, basically. Okay, so we're going to have a function that looks like this. So when we say dynamics, we mean this function, this f. This is called the dynamics. Oops. And it's a function that takes in a state vector. So that's the x. It's called a state. And in our case, because we're doing control stuff, the u here is the input or the controls. So these two things are vectors. So we generally say the state is a vector in Rn, so n-dimensional vector. And then the input is in general, different size vector than the state. And we usually use m for that dimension. So Rn, Rm. Unfortunately, those sound very similar. So it's confusing when it's said out loud. And then this guy, x dot, this is the time derivative of the state vector. So this is a first order ordinary differential equation. That's what this is. You're maybe, if you've taken a basic dynamics course and you've seen like F equals MA, Lagrangian stuff, that's a second order ordinary differential equation, right? So A is, Q double dot, right? It's second derivative, it's acceleration. So, but we can always write this stuff in this form of a first order ODE. And I'll show you exactly what I mean by that. So for a mechanical system, like most robots, right? And it comes down to how you define the state. So for a mechanical system, like, I don't know, pendulum, pick or most robots, the state vector X includes the configuration or pose. So this might be, the position and the joint angles, right? Everything that describes the pose of the robot and the velocity. So by writing the state vector that way, now x dot includes v dot, which is the acceleration, right? So that's how we get it to be from a, say, second order F equals MA type thing into a first order vector ODE by sort of including, basically by making the state vector twice as big. So this guy up here is called, the Q is called configuration. That's sort of the physics word. And then pose is kind of the robotics word, but you'll hear both kind of interchangeably. This is importantly, which we'll get into a little bit, this Q is actually not always a vector. i.e. it doesn't always live in a vector space Rn. It can be more complicated and weird than that. In particular, does anyone know kind of a case in which this is not a vector or is something weirder? Hmm? Yes, so not so much. I mean, like you can stack up a vector of joint angles, right? So in particular, what I'm getting at here is like if I talk about rigid bodies and I talk about orientation, like we have position and then we have attitude, right? Orientation. So attitude is not a vector. Like you can write it as like a stack of 3 or 4 numbers or whatever, but those don't add like vectors, right? So if you do like roll, pitch, or if I switch the order and do pitch, roll, I get to 2 different orientations, right? So that's does not add like a vector. So that's a more complicated, weird group thing that we're going to talk about in the class, like because it's super relevant to robotics, but it's more to come on that. It's a weird thing. So this is, just to be clear, this is not always a vector. It can be some more complicated Lie group or manifold thing that has more structure, which we'll talk about. And then this V down here, this is the velocity. So fun fact, even if Q is not always a vector, V always is a vector, which is kind of weird and like not obvious why that's the case. More to come on that. We'll talk some more about it. Okay, so this is what we mean by dynamics. This is what we mean by a state vector. Basically, the state vector is everything you need to specify. The real definition of a state vector, it's everything you need to specify the initial conditions of a system. That's what it is. So in general, that's like a position and a velocity, pose and velocity, that kind of thing. And then you can write your dynamics down like this. So whatever you've got, no matter how you got it, you kind of stack up a big state vector such that you can write down some big nonlinear f of xu like this. Okay, so now we're going to do a concrete example just to kind of make everyone feel good and show you something that I'm like 99% sure that 99% of you have seen before. So we're going to write down a pendulum. Okay, so again, I expect that you've all seen this before. So we've got like some kind of, ground ceiling thing. We've got a mass. We've got a length. And we've got an angle theta to describe the pose. And if you've, taken any kind of dynamics course, freshman physics, whatever, you've seen this before, right? So the dynamics of this guy, as hopefully we all know, I'm not going to derive it, looks like this. Got like ml squared theta double dot plus mgl sine theta. And since we're control people, we're going to have a torque on the other side of this so that we can control it. Okay, so yeah, again, in this class, we're not going to make you derive this stuff. We're going to give you the equations, but you're going to have to work with the equations. So this is, hopefully you've seen this in freshman physics. So now what we're going to do is massage this into this f of xu form up here. So right now, this is like I did f equals ma. I've got a second order ODE. So we're going to now map this into the stuff we just saw. So in particular, what's our Q? Good. Q is theta. What's our V? Theta dot. And what's our U? Tau. Okay, cool. So now we've got kind of the variables figured out for this standard form. So now our X is going to be theta dot. And our dynamics equation is going to look like X dot, which is theta double dot equals, and then the top one's trivial because that's already in the state vector. So that's just theta dot. And then the bottom one, I'm going to take that ODE and just massage it around to solve for theta double dot. So this is going to turn into minus G over L sine theta plus 1 over ML squared U. So this now, this like vector equation is my f of xu. So this is my dynamics. Cool. Questions about this? Yeah.
I think your V is supposed to be theta dot.
It is. Oh, yeah. Thank you. Okay, cool. Anything else? Did I do anything else stupid? Okay, so now we're going to like throw you some fun stuff. that maybe you haven't seen before. So I mentioned this little teaser that Q is not always a vector. It can be other weirder things. So does anyone want to tell me what the Q is in this case for a pendulum? Like topologically? Yeah. Yeah. So it's not Rn. It's not the real line. It's actually a compact manifold. It wraps around. It doesn't go to infinity. It's a circle. Yeah. So this is like, in this case, kind of trivial and not super important. You kind of pretend that's not a thing. But there are many, many real life cases where you actually have to reason about this sort of manifold structure, and it'll bite you, particularly for our purposes, attitude in 3D. You actually have to worry about it. So yeah, in this case, even the simplest problem you've ever, dealt with, like the simplest nonlinear system, there's more going on than you probably learned about in freshman physics. So here, the configuration space is not Rn. It's actually what we call S1, which is the circle. Okay, more fun. What is V? Where does V live? So the Q is a circle. What about the velocities? So yeah, the velocities are R. So the velocities can be anything, right? So that really, it can take on any number on the real line. Cool. So what's the state space topologically? So one coordinate has to live on a circle, right? And then the other coordinate can be the entire real line. Yeah. So have you guys seen this before on this kind of stuff, on like geometric mechanics? Okay, it's fun stuff. Okay, so anyway, yeah. So X then is, so the way to think about this is you've got a cylinder, or you've got a circle for the theta. So one point of X has to be on that circle. Then in every point on that circle, you've got a velocity that can be anywhere along this real line. So if you put those together, it makes a cylinder. So this is in kind of fancy notation, you call this S1 cross R. Okay, lots of fun stuff. Okay, questions about that? Cool. So that is generic continuous time dynamics, f of xu. You can always write mechanical systems like this, figure out what your state vector, massage your equations around, boom. So now we're going to start talking about more specialized classes of dynamics, where there's more structure we can take advantage of. So the next more specific class of systems are called control affine. Anyone heard of this before? Show of hands, like 2 people. Okay, now we're into some new stuff. So what these things look like, so these are still nonlinear systems in general, but they look like this. So they have a term that we'll call F naught that's just a function of the state. So this is a nonlinear term. And then they have a term we're going to call B of X, where B is a matrix that's a nonlinear function of X times U. So the idea here is this is a nonlinear system. It's nonlinear in the state, but it's linear affine in the control input. Make sense? So that's how U enters. Yep. And affine, so this is control. So affine means linear plus a constant, right? Everyone, so AX plus B, right, is affine. This is called control affine because while it's nonlinear in X, like F and B are both nonlinear functions of X, if I fix X and just think about it as a function of U, F naught is a constant, B is a constant, right? And so it's just F plus B times U. So it's in terms of just U, if you freeze X, it's an affine equation in U, right? Makes sense? So this is called control affine. And these things have names. This first term that just depends on X is called the drift term. And then this B over here is called the input Jacobian. Okay, so why are we even talking about this? Turns out this is super useful in control stuff. This shows up a ton in classical robot manipulator stuff. And it turns out that pretty much every mechanical system can be written in this form. So most systems that you would care about, basically, can be written like this. And in particular, if we go back to everyone's favorite nonlinear system, we'll do the pendulum. Just from like the stuff we showed, above, we won't belabor this, but I'll show you the drift term. Looks like this, theta dot minus G over L sine theta. And I'm just picking the terms out of here. Basically, all I'm doing is taking that and factoring it out, factoring the U out, right? So that's your F, and then the B, the input Jacobian, is 0 and then 1 over ML squared. So it's not immediately obvious maybe why this is useful. We'll get to it later, but you should know it shows up a lot. It's convenient, and most of the systems you're going to deal with, even if they're nonlinear, are actually control affine. Okay, cool. So that's cool. Next, more specific class of dynamics. Yeah. No, because in general, right, I have a fixed x. F of x doesn't have to be 0, right? This F naught, even if x is constant, the F naught is not 0. And the B times U, if U is non-zero, that term is non-zero. Right? So it's non-zero in general, right? Even if x is fixed. So the real magic of this, and the reason this is worth talking about, is if B is full rank, I can invert this equation and solve for U such that I can make x dot arbitrarily anything I want. Does that make sense? So that's called being fully actuated. And that's a classic trick that's done all the time in robotics called feedback linearization. It's basically how you control classical manipulator arms, right? So that's why there's a thing. And we'll get into it more later, but that's basically it. If that B is full rank, you can kind of make the system do anything you want. And it's sort of controlling its trivial, right? That makes sense? Okay. Foreshadowing and fun hints. Okay, any other questions? Cool. Okay, so next, more specific class of systems that we will see all the time that you should know about, especially if you're a roboticist, are what are called manipulator dynamics. Anyone heard of this before? Show of hands. Good. Yes. So if you've seen this before, you have seen control affine before, because this is control affine. So here's what manipulator dynamics look like. We've got a mass matrix that's a function in general of the pose or configuration, m of q times v dot times acceleration. We have this C term, which is kind of called Coriolis or dynamics bias. It's a function of q and v. And then on the other side, we have an input Jacobian times u, and then we can have other kind of generic forces. So I'll label all these. So this guy, M mass matrix. This C term is called, often called the dynamics bias or dynamic bias, which includes kind of Coriolis terms and gravity. And then B is again input Jacobian. And then this F over here is just kind of any other external forces on the system. Like anything except your control inputs, basically. It could be contact forces, could be anything else, right? Okay, so in addition to this, so this is the dynamics. If we want to write down the full state equations for the system, we also need another piece of the puzzle, which are these kinematics. In general, those can be complicated. So far we've seen stuff where q dot equals v, and that's kind of trivial. In general, q dot can be a more complicated function of v. We're going to see systems that look like the following. There'll be some kinematic Jacobian g that's a function of q times v. So in general, q dot can be some sort of function of v. Make sense? Anyone know where that shows up in particular? Anyone seen that show up before? Yeah.
Wait, I was gonna say attitude, but I'm not sure.
Yeah, totally. So it's anytime it's anytime that the velocities are not the q dots, which shows up if you use a quaternion. And so if you have a quaternion that's 4-dimensional and you have an omega that's 3-dimensional, obviously q dot doesn't equal omega, right? So it looks like that. Or if you have a rotation matrix and you have an omega, right? So they're different objects. So you have to kind of impedance match your like angular velocity into your attitude representations. That's what this is all about. So that's one version of it that shows up in many kind of general settings. Cool. Any questions about that? All good? Okay. So yeah, this thing, we'll call this the velocity kinematics. And this again shows up a lot when you have attitude. That's kind of generically where we see it. And then if you've got this, you can always very easily turn it into our generic f of xu as follows. So up here, you've got just your velocity kinematic stuff up top to get q dot. And then v dot, you're just going to basically invert the mass matrix and then move everything else over to the other side. So you can always get it back into that form. Questions about that? Cool. So back to everyone's favorite nonlinear system, pendulum. We'll put it in this form. So for a pendulum, again, we're just going to go back up here and like refactor a little bit. So for the pendulum, the mass matrix, also if you're fancy, you can call this the generalized inertia tensor, is ml squared. If you've taken any kind of mechanics course, what is ml squared? Inertia. It's the inertia of the pendulum, right? Okay. The Coriolis term here, I guess Coriolis gravity, whatever, is mgl sine theta. The input Jacobian is just an identity. And in this case, if we've got theta, theta dot, the kinematic Jacobian is also just an identity. So easily we can put the pendulum into this manipulator form. Why do we care about this manipulator stuff? Number one, all mechanical systems can be written this way. So i.e. pretty much all like multi-body, rigid body robot systems can be written this way. Anyone know why that's true? Why does that have to be true? You have any insight? You're getting close, yeah. So this kind of looks like F equals ma, right? It looks like a weird sort of generalized version of F equals ma in some sense. It turns out this manipulator equation is literally the Euler-Lagrange equations, just massaged around with names given to the different terms. So this is literally, if you've taken a Lagrangian mechanics course, this is just the Euler-Lagrange equations. So that's all it is. And that is why any Lagrangian system, if you can write a Lagrangian for it from like a classical mechanics perspective, you've already got the manipulator equation basically. And in particular, so that's true. Let's see. This is just a way of rewriting the Euler-Lagrange equation. In particular for the following Lagrangian. So I have, right, it's kinetic minus potential energy for those of you who've done this before. This is just kind of fun fact stuff. I have a kinetic energy that looks like this. And then a potential energy, which we'll call U to avoid notational overloading. That guy. And I kind of turn the crank on the Euler-Lagrange stuff, I get the manipulator equation. Bonus point for anyone who actually wants to go derive this and show that they're equivalent. Throwing it out there. Okay, so yeah, this is the kinetic energy, right? And this is the potential energy. Cool. Questions about that? The other big reason why we're talking about this, by the way, is that all the robotics toolboxes do dynamics in this form. So you kind of, if you're going to use any of the software toolboxes that do dynamics, you kind of just need to know how to work with this stuff. Yeah. So this is a fun one. Can anyone tell me about this M matrix? There's certain things that have to be, this M matrix has to have some structure to it. And it's sort of obvious from this kinetic energy. So based on this kinetic energy right here, can you tell me something about that M? It's so, yeah, basically some people threw it out. So basically this M, it corresponds to like a mass, right? It's basically just a mass rewritten in weird coordinates, in joint space coordinates in general for us. And because it's mass, it corresponds to a quadratic form here. So because it's in that quadratic form there for the energy, it has to be symmetric. That's like a given. It turns out this M has to be symmetric, positive, definite. That kind of comes back to the fact that if you look at this energy thing from a basic physics perspective, I can't have negative energy. Not a thing, right? I can't have negative kinetic energy. So from some basic physics arguments, it's pretty easy to see that that M actually has to be symmetric, positive, definite, aka always has to be invertible. You can always invert M. You can make life hard for yourself by choosing a bad set of coordinates, in which case n can become ill-conditioned and or have zero eigenvalues and be singular. That basically comes from introducing redundant coordinates that like don't do anything. Then you can have zeros in there. But in general, if you do things properly and don't make life hard for yourself, m's always going to be invertible. Any other questions? Yeah.
Why is input Jacobian a function of one of the state space?
It's a function of the configuration. So for a mechanical system in particular, so control affine is a more general thing. We say B of X. For a mechanical system, it's only a function of the Q's. This is basically an artifact of like Lagrangian mechanics and like how that looks. So if you kind of write down the Euler-Lagrange equations, it just kind of falls out that way. I'm trying to think of a like better way to say this. This is, yeah, you know what this actually comes from? It comes from the potential energy thing. So like if you have a kind of conservative force, it's not a function of velocity. Even non-conservative forces. So like if you have like something that's like, I don't know, air drag or something like this, or friction, that will be velocity dependent, but it doesn't fit into this kind of form, right? So like joint torques and stuff like this, I don't know, that's kind of the way they enter the equations, but other things can be velocity dependent. We're just kind of shoving that into that F. So I don't know, it's basically the way we've structured these equations. We've pulled out, you know, the stuff that is, that corresponds to like joint torques and thrown them in there. And anything else, we're just throwing in the F, anything that doesn't fit that recipe, so to speak. I don't know. It's a little bit of a, I don't know. We've chosen to write it this way kind of thing. I don't think there's anything deep behind that. Okay, anything else? Cool. Let's see. What else are we going to talk about? So we're getting short on time. Another class of systems that we're going to spend a lot of time talking about that are like bread and butter of controls that you should absolutely know about are linear systems. Who's taken a linear systems theory course? So like quarter of you. So we're going to do some more crash course material on this stuff. These look like the following. X dot equals A, which in general can be a function of time times X, plus B, which again can be a function of time times U. So this thing is called time invariant, linear time invariant. If the A of t is a constant and B of t is a constant, called time varying otherwise, linear time varying. These are like the bread and butter of control theory. So you're going to see this stuff a lot. And one of the reasons these are so popular, they're really useful for analysis and for control design, in particular because if we ever run into a nonlinear system, as long as it's smooth, we can always take derivatives and linearize it and approximate it as a linear system, which we're going to do all the time because it turns out that works really well, like 80, 90% of the time. Say again? So yeah, like if your dynamics are linear, you can write the control problem down as a convex optimization problem. Yeah, so we're going to talk about that too. So we often approximate nonlinear systems with linear ones locally, right? And the way that works is if I have x dot equals f of x comma u, then if I want to write that as I want to approximate that by a linear system, the A matrix is just going to be df dx. And the B matrix is just going to be df du. So if I want to, kind of approximate my system locally about some nominal x and u, take the Jacobians, now I have a linear system that I can use to analyze the behavior of the system locally and to design local controllers. Okay, there's a little bit more to talk about, but I think we'll save that for next time. I don't know. We got 5 more minutes worth of stuff. Yeah, that's correct. Yeah, that's right. So yeah, we said that control affine thing, that was linear in the U or affine in the U, but non-linear in X. This thing is linear in both X and U. It's completely linear, right? Which obviously makes life easy because now we can sort of do all the things with linear algebra. We know how to do linear algebra, and we know how to get the answers and stuff. Okay, on that note, we're out of time, so I'll do the last couple things in here next time. Welcome. Thanks for joining us. It should be fun. See you guys next time.